Okay, great. Welcome to Nuklearia Stammtisch, or more or less monthly or twice a month since recently occurring online meetup. Okay. Yeah, I'm pleased and honored that we can welcome you to share information about your technology. And I think we can start.
Debate. 30 years ago, it supplied less than 1% of global energy. Now it supplies less than 2% of global energy. So it's actually a very small contributor, even though it's 90% of the debate. If you go back even further and look at how humanity got our energy now, of course we started with the traditional biomass burning wood. It's actually a very small contributor. And then we learned to use coal and later oil and gas. Also from this chart, if you go back even further and look at how humanity got our energy now, of course we started with the traditional biomass burning wood. It's actually a very small contributor. and then we learn to use coal and later oil and gas. Also from this chart, if you go back even further and look at how humanity got our energy now, of course we started with the traditional biomass burning wood. It's actually a very small contributor. And then we learn to use coal and later oil and gas. Also from this chart, if you go back even further and look at how humanity got our energy now, of course we started with the traditional biomass burning wood. In general public, we always get this feedback that nuclear energy is very costly, it's always delayed, takes many years to build the power plants. A lot of them say that it's dangerous, even though we know it's clearly not dangerous. And a lot of them complain about the waste problem have not been solved, which is hardly correct, but there's definitely something that should be included in the debate, and we want to be part of that debate about nuclear waste. The long-term purpose of Copenhagen Atomics is to build molten reactors on an assembly line, and we want to configure them as waste burners so that we can burn some of that spent nuclear fuel from classical nuclear reactors. And our the model that we're working towards is 100 mega. A lot of them say that it's dangerous, even though we know it's clearly not dangerous. And a lot of them there was a little reverb. I hope you can still see the slides. Maybe I should just check the chat. All right, it seems okay. So this image shows sort of what we are aiming to build in Copenhagen Atomics. It's a 40-foot shipping container sized box. Inside the box is all the radioactive parts of the reactor, and it's 100 megawatt thermal energy. And this box can burn spent nuclear fuel from existing reactors, and I will get back to how that is a little bit later. We want to think about like how quickly could we potentially install nuclear energy, and in order to give sort of a big introduction to that, we want to start here. This is one of the very first reactors that was ever built by humans. It's the Hanford B Reactors, built part of the Manhattan Project. It took 11 months from they broke the ground till the reactor was up and running the first time. At that time, they didn't have computer simulations. There was a lot of the physics behind nuclear fission that was not well understood. And this particular power plant is actually rather big. It's a 2.2 gigawatt reactor. There was 5,000 people involved in constructing it, and it ran for 25 years without any accidents. So, I mean, clearly we humans are capable of building big reactors in 11 months and getting it up and running, even when we have almost no knowledge about how it's supposed to work. And then you contrast that to one of the newest reactors that we are currently building in Europe. This one is a Reactant Finland. They started building it in 2005. And now 17 years later, it's still not in full operation. It's a little bit bigger than the other one we looked at before. It's a 5 gigawatt plant. Its expected lifespan is 80 years, and there's almost 4,000 people and 500 companies involved in building this. And maybe there's a clue to why it takes so long when you see that there's 500 companies involved. But it's not for the people like us who like nuclear energy. This is sort of not a good storytelling because it's been delayed many times. There's been cost overruns, and it's not new technology. I mean, this type of reactor has been built many times before, or at least something very similar to it. So it's not like we have to learn a lot of new things. And now I have this table, which is a comparison between classical reactors, or the type of reactor we just saw in the image before, and the type of reactor that we want to build in Copenhagen Atomics. We call that the waste burner, so that's the one at the bottom of the table. First of all, when you want to use uranium, enriched uranium 235, you need to do a lot of mining to get all that uranium out of the ground. So compared to the amount of mining and materials you need for Copenhagen Atomics waste burner, you need 100 times more mining operation for light water reactors per energy unit you produce. And again, you need enrichment, and we don't need any enrichment for our reactors. Enrichment is a lot of times it's very expensive. It requires very pure materials or uranium to do that, and very expensive. And then there's the proliferation risk related to that, which some of the people in the public think is a major issue, and so that's part of the debate. And then, of course, when you dig a lot more things out of the ground, there's also going to be a lot more waste, because essentially light water reactors are not very efficient at burning all the fuel you put into them. So that means the waste volume is large. The type of waste that is left over after the end of life of the reactor, spent nuclear fuel, in general, people say that it needs to be stored for 100,000 years. Of course, that's debatable, but many people agree that it needs to be stored for many, many years. In contrast, what comes out of the Copenhagen Atomics waste burner is mainly only fission products, and fission products sort of only need to be stored for around 300 years, and we humans already know how to do that. In terms of energy price, because we are able to manufacture these reactors on assembly lines, and because the amount of materials that goes into these reactors are much smaller, and because it's not a new design every time we start over, and it's not a new team of people who are going to build it, it's the same team of people that are building every one of them, and it's a factory assembly line process, so we can reduce the cost of roughly 10 times what it costs to build a classical nuclear power plant for the same amount of energy output. And then the deployment speed is, of course, much faster, because we can make these in a factory, and there can be hundreds of companies constructing the power plant. If it produces electricity, for example, there can be hundreds of companies around the world producing the power plant, and then we just come with a reactor and embed that into a power plant. So it's a little bit like a coal-fired power plant, where we are only putting in the burner or the flame. The rest of the power plant is built by somebody else. But again, I'll get back to that. And the final column there in the table is about efficiency of converting heat into electricity, because molten salt reactors run at much higher temperatures. You can get a better efficiency when converting the heat into electricity. Many times people also mention what is the difference between what is the difference between thorium molten salt reactors and uranium-based molten salt reactors. And it's not been explained very clearly by many of the presentations, so therefore I included this. Of course, clearly, if you run on uranium, or especially enriched uranium, for your molten salt reactor, you get maybe a little bit better efficiency and burn up, but the amount of material you need to mine is still much larger than if you run on a thorium fuel cycle. You still need the enrichment, and you still have the same type of waste as you do from a classical nuclear reactor, whereas the last three columns are the same as in the previous slide. So a lot of times when people debate nuclear reactors, they only talk about electricity production. But it's actually a shame, because especially for molten salt reactors, they are very well suited for also providing energy for all other sectors. Today, if you look at the world, the energy production in the world, only roughly 15% of energy in the world goes towards electricity. But a lot larger energy goes towards industrial heat. And we also believe that in the future we're going to go away from gasoline and traditional diesel and start to produce more synthetic fuels, such as biodiesel, ammonia, and those types of synthetic fuels. And for producing these fuels, you also need energy, and a molten salt reactor is a very good input source for that type of energy, and convert the energy into storing it in synthetic fuels. And finally, of course, you can use it to create fresh water, water desalination, and even wastewater treatment. And then also, when you look at the technology that we are building in Copenhagen Atomics, we do not only look at this technology as something that can be used for molten salt reactors, or specifically for the Copenhagen Atomics waste burner. The technology that we are developing can actually be used for a number of different industries, and we already have collaboration with people from a number of different industries. So, for example, molten salt energy storage, which I think will become rather big here in the 2020s. There's also concentrated solar power plants. Those are the ones where you have a lot of mirrors out in the desert pointing up towards a tower, and then you heat salt up in that tower, and that creates energy. And of course, there's geothermal energy using molten salt. Now I want to talk a little bit about what are we doing in Copenhagen Atomics. So we started back in 2015, but 2017 was the first time that we did a public demo with some things we had built. And then in 2019, we started testing a lot of the components that are needed for molten salt reactors, and that's sort of still the main activity that is going on in Copenhagen Atomics. We're currently designing and building our first non-fission prototype that is supposed to be ready by the end of 2022. And while we do that, we continuously test a lot of the components, such as pumps and valves and heat exchangers and gaskets and all kinds of different measurement systems and sensors and so on. And then finally, when in 2022, when we have built a one-to-one scale of our first test reactor, then we are going to find a country where we will test that reactor. And then once we've selected a country, then we will start to get the approval. And we hope that by 2025, that approval will be in place and we're able to start our first molten salt test reactor. The reactor that we start in 2025 is, of course, sort of a test reactor to show that the technology is working. It's not going to have all the bells and whistles that one could wish for in a commercial reactor, and also it's not going to produce electricity. And as soon as we have launched the first test reactor, then we are going to, of course, continue to develop our first commercial reactor, which is supposed to go online in 2028. And that's going to take a number of years both to design it, but also to get it approved. Most of that effort is actually for the approval, since we've already demonstrated that we can run a reactor before that. And I want to point out also how Copenhagen Atomics is different than some of the other players in the nuclear industry, or especially sort of the old-fashioned design method. So, some companies want to make what is called a paper design, where they sort of make CAD drawings and 3D renderings and nuclear simulations and a lot of documents about how this reactor is going to work. And when they have produced thousands and thousands of pages of document and drawings, then they go to some country's regulator and they say, please review all these documents and tell us if we can be allowed to test, build this reactor and test it. And then, of course, they get some feedback, and then they have to sort of maybe update the design a little bit. But eventually, they hope that they get a design approval, and then they will start building the reactor. In Copenhagen Atomics, we sort of take that whole process and turn it upside down. And the reason we do that is because we know that once you have spent all this time on designing a reactor, and then you have gone through an approval process, and maybe eventually you have a full approval, and then you start building it, it's going to be really, really difficult if you learn something while you build your first reactor. It's going to be immensely expensive to go back and change those documents because you've already gotten them approved. So every little change is going to cost you like $1 million or something. But so that's why we approached this differently. We said we want to test all the subcomponents. We want to test all the systems before we go into the approval process to make sure that we know that they function like they should. And we've optimized some of the obvious things that we learn through this process. And that's why we have these rapid loops where we improve the technology. And we can do that because we don't have to ask anyone. If we find out a valve is the wrong size or something else, we can change it. It only takes a couple of weeks or maybe a month to get some new components and get them and implement them and test them. So it's much, much cheaper and much, much faster to do new technology development in this fashion. And then once we are happy with the design, and that's sort of around 2022, then we will start the approval process. And of course, when we start that process, our design will not be able to change as much anymore. But I believe also when we're going to build commercial reactors, we will use the same approach where we first design the entire reactor without going through the approval process, and then we will validate and test that all the components and everything is working correctly as we expect in our own internal reviews. And then once we have like a full design that we are happy with, then we go to a regulator. It's also from the regulator's point of view, it's much easier to prove something where you can actually go out and ask the developer to run some tests, and you can see the results of those tests with your own eyes. it's much more difficult to determine when you've read like 1,000 or 10,000 pages of documents. It's much more difficult to determine whether everything in those documents are correct. I mean, from the regulator's point of view, it's less of a risk to approve something that has already been built than something that's going to be built from a set of documents. So that's the reason why we chose that process. Another reason is, of course, that we believe that it's much less costly, so it's a better deal for the investors. But that's also, just a great side note. Copenhagen Atomics have been fortunate to be invited to rent some space in collaborate with Alfa Laval. Alfa Laval is one of the big industrial companies that makes things for the food and water industries, and for energy sectors, and for the marine sector. And they have, at the site where we are located, they have 600 employees building some of the things you can see in the background there in this image. The things in the foreground here is our molten salt test loops that they also manufacture, and some of the tanks that we are using for molten salt energy storage and testing. Again, same picture from the same workshop. I want to stress this philosophy that we have in Copenhagen Atomics, where we want to build things, test them, and then learn something, and then iterate back and build and test again. We believe it's really, really important in order to learn and launch this new type of technology. And one of the things we're really proud of that we've made in Copenhagen Atomics is this pump that you see there in the image. This is actually one of the first versions. We already moved on to third and fourth version of that. But it's a unique pump because it has no seals. This means that it cannot leak anything during operation. And why is that important? That's of course important because we pump highly corrosive, highly radioactive materials, where inside these salts there's also gases that nobody wants to see escape out of the primary loop. So therefore it's really, really important to have a pump that does not have seals or gaskets that can wear out. So we've been very fortunate to be able to develop this pump, and we've taken many patents on this, and it's actually something we believe will help the entire molten salt industry to move forward. Because if you look at the molten salt reactor experiments in the 60s and look at the pump they had back then, this pump definitely solved some of the problems that they talked about in their reports that they had issues with in the pump that they used at that time. Also, on the very right-hand side, you see an image of one of our molten salt test loops. This is the 5th generation test loop we've had. Of course, a number of generations before that, and we're already working on sort of the next version 6 of that. And these test loops are sort of a platform that enables us to test all kinds of components, pumps, heat exchangers, valves, sensors, and all that good stuff in real world scenarios. And actually, I should also mention that the pump that we're building now and testing is the one that has the right size for the 1 megawatt reactor. Later on, when we want to build the 100 megawatt reactor, we will scale up that pump, but we're not ready for that yet. This is the building that we are currently located in. Well, there's actually several buildings, but this is the building that house our office facilities and our chemical labs facilities, or salt lab facilities. And here are some of the images from the sort of the factory floor with the production area, and where we have also the testing of components, assembly of components. And there, a little bit later, there is a video, or maybe I should actually play that now. Let me just swap over, see if I can. I don't know, can you guys see this video that is on the screen now? Okay, it might be that I should share a different screen here. Change window, yeah, I need to change that. I think, did this help? Okay, welcome to this virtual tour of the Copenhagen Atomics workshop area and test facility. We are located inside this big building. It's an industrial site which we rent space from Alfa Laval in Copenhagen.
And there's plenty of space to expand here. Right now, right next to me, we have 1,000 square meters of area for building molten salt test loops. Over there, you see 7 test loops being, some of them are under test, some of them are being built or rebuilt. And just in front of me here, or just behind me, we have test tubes that we're building. We're currently building 20 of these test tubes in a batch, and they are for testing molten salt, stable molten salt for corrosion and other things. Further up in the background, you see our workshop area where we have a lathe and laser welder and some of these equipment. If you look down in this direction, we're currently expanding down there with another 1,000 square meters for pump production and other component manufacturing. And you can see that this workshop area can be expanded to also produce molten reactors in 20-foot shipping containers, so that this is more or less, this can easily be adapted for assembly line production.
There were some messages while I was playing the video. I don't know if everybody could see it, but at least I got the impression that some people was able to see it. So I hope that was working. Otherwise, I hope the YouTube, the video recording was able to catch it, so that maybe some people can go back and view it later on. Otherwise, I can try at the end of my presentation, I can try to play it again. Okay, thank you for the feedback. Of course, there were some questions ahead of this this talk where people were asking why do we want to use thorium and some of these other questions, and I will go into that now, more sort of a little bit more technical details. I don't know if all of you know the thorium fuel cycle, but I'll try to explain it just quickly here. That you, at the bottom of this drawing, you have the thorium which you dig out of the ground, and in contrast to having uranium in light water reactors, it does not have to be super pure like it does in light water reactors. And then you put that thorium into your salt, and it's dissolved inside the salt, so it actually becomes an element that is a structural element of the salt, you could say, or one of the metals in the salt. And then you have a lot of thorium in a reactor, like more than a ton maybe. And then it's when one of these thorium atoms is hit by a neutron, especially a thermalized neutron, that means a slow-moving neutron, then the thorium atom is likely to capture that neutron and change to a thorium 233 atom, and you can see that on the 9 o'clock on this chart, and that will then decay down to protactinium 233. This happens rather quickly, and then protactinium 233, which is at 12 o'clock, will decay slowly into uranium 233, and this decay from protactinium to uranium, it has a half-life of roughly 30 days. So this happens slowly, and then once it has converted into uranium 233, and that uranium 233 is then hit by a slow-moving neutron, then the uranium 233 will split or will fission, and that creates a lot of energy. That's supposed to be the red arrow that indicates the energy, and then of course uranium 233 releases on average 2.3 neutrons in thermal spectrum, and it's those 2.3 neutrons that is really important, because that is what allows us to run a chain reaction. And then of course you need a moderator to slow down those neutrons, and in Copenhagen Atomics waste burner design we use heavy water as the moderator, and I will get back to why that is. And now we want to talk about what is a waste burner. So this chart here is a little bit busy, but it shows the fuel pins of a light water reactor, which is most of the spent nuclear fuel that we have in the world today. And a fresh fuel pin, which is on the very left side of that chart, shows that many times this fuel is enriched to 3%, or a little bit above 3% of uranium-235. And then when we start burning it inside the reactor, then of course you generate some fission products and you burn up the uranium-235. So you can see at the top that you have less and less uranium-235, and then more and more fission products, which are the gray area. But while you're burning up that uranium-235, some of those neutrons also sort of breed the uranium-238, which is a dark blue colored, into plutonium, different types of plutonium, and also other long-lived actinides, but the plutonium are the major components here. And some of that plutonium, especially the plutonium 239 and 241, they can burn also in these light water reactors. So a little bit of that plutonium is burned over time, and that's actually what is indicated here, because some of that also turns into fission products, which are the gray ones. So this kind of gives you an idea how fuel inside a light water reactor is burned and what you have left afterwards. And what you have left is sort of this pie chart in the middle. So you take the used nuclear fuel and you see that roughly 95% of that is uranium. And that uranium is exactly the same uranium as we dug out of the ground many years earlier when we did the mining. And we already know how to process uranium, because we make very, very pure uranium when we need to do the enrichment for the fuel in the first place. So we already have the processes in place that can extract uranium in a very pure form. So of course we can also do that with spent nuclear fuel, and that pure uranium can then be sold back to the global uranium market. And then you have the remaining there, the 4.4%, and those of course what creates all the trouble. Those are the 3.3% is fission products, and the fission products they can be stored in a safe way. We humans already know how to do that, and they need to be stored for roughly 300 years. And then after that, the radioactivity is very low, and it would be safe to release them back out into nature. And then, of course, the last little bit, the 1.1% of this chart, is long-lived actinides and plutonium. And this is the stuff that basically creates a problem for spent nuclear fuel in the first place. So, and it's expensive to separate that out. But the great thing here is that we can put that 1.1% into the Copenhagen Atomics waste burner, and then we can burn those actinides and use the plutonium as a kickstarter fuel to get the thorium fuel cycle started. And over several decades, these long-lived actinides will eventually burn up in that process and again turn into fission products. And we already know how to store fission products in a safe way. And now the question of how does this work from a nuclear physics point of view, because some of the questions we get every now and then is, why don't you use a fast reactor? A fast reactor is much better at burning long-lived actinides, and that's sort of true. But you also have to look at the economics and who's going to pay for all this. And as you can see from this chart here, I want to remind you that on the y-axis, it's a logarithmic scale. So the fast spectrum, if you look at the arrows down at the bottom, their sort of fast spectrum is from roughly 1 mega electron volt and upwards, and the thermal spectrum is all the way down at the left side of the chart. And you can see that the chance of having fission when you hit an atom with a neutron, it's almost 1,000 times better chance of having fission in the thermal spectrum or on the left side of the chart than it is on the right side of the chart. And of course this means that you need a lot less fuel in order to make this work. And especially for plutonium-239, it works particularly well in thermal spectrum. And as you saw in some of the previous slides, most of the long-lived actinides in spent nuclear fuel is actually plutonium-239. And some people have even told us that, hey, it's impossible to burn long-lived actinides in a thermal reactor, but I mean this shows you otherwise. And I'm also sure that people agree that both plutonium-239 and plutonium-241 will readily fission in thermal spectrum. And I think also people will agree that even in a thermal reactor, you also have some percentage of your neutrons that are fast neutrons, because all neutrons are born fast right after a fission event. So yeah, so you will always have some percentage of fast neutrons. And of course, if you have to calculate the chance that they will hit one of the actinides, and of course, then it works the same way as in a fast reactor. And also why we want to use thorium. It's again, if you look at this chart, thorium is the red line, or that's not entirely true. Uranium-233, which is the product of the thorium fuel cycle, is the red line. And especially for thorium-233, it works really well in that area of the spectrum where we are interested in running our reactor. And the thing you see here is that on average you get 2.3 neutrons released from every fission, and that means it's possible to have a chain reaction ongoing, and not only possible to have it ongoing, thorium is likely the only fuel on this planet that makes it possible to have a breeder reactor in thermal spectrum. None of the other materials can do that. And when I say it's possible, of course, it's from physics point of view. We know it's not easy at all, and we don't expect neither the first or the second version of our reactor to be breeder reactors, but it is something that we would like to pursue in the long term, because it makes it possible to have nuclear energy without doing enrichment, and we believe that is actually a really important thing. I need to check one of the last. Okay, so I want to say one more thing here is a lot of people say that fast reactors are better breeders, and from this point of view of this chart, it is true that you get more neutrons per fission in the fast spectrum over here on the right side of the chart. But you also have to remember that you need a lot bigger fuel inventory in order to make the whole process go. And on top of that, you have to see that we humans have built almost 1,000 reactors in the thermal spectrum. Almost all of those reactors worked in the way they were expected to do. And we humans have built something like between 20 and 30 fast reactors throughout the last 60 years. And there was basically none of those fast reactors that became a commercial success. And that just tells you that it's much more difficult to build fast reactors, and probably it's going to cost much more. I mean, whether it costs twice as much as a thermal reactor per the same energy unit, or whether it costs 10 times more for the same energy unit, that is not clear yet. But it's the way I think about it is that thermal reactors, that's really simple. The very first reactors we built, like I showed the Hanford reactor, they were able to start right away, and they worked for sort of like 25 years or even more, some of them. This is easy stuff. It's something that humans have showed again and again and again, and across many different countries, that this is something we can do. It doesn't create a lot of technical hurdles. A lot of different countries have tried to make fast reactors work, and none of those countries have been very successful in the fast reactor development. It's not to say that they won't be successful in the future. I'm just talking about what happened in the past now. And then finally, we have, of course, fusion, which is sort of, a lot of people is looking to fusion and say that it can solve a lot of problems, but I think fusion is even more difficult. So it's sort of like thermal reactors are simple, fast reactors are in between, in the middle, and fusion is really difficult. That's my view of things. And of course, I acknowledge that other people might have other views, but this is the reason why Copenhagen Atomics chose to pursue a thermal reactor. This chart here is talking about coal-fired power plants, and the reason I wanted to include this is because, of course, we see that if we don't build nuclear reactors, then most countries will build coal-fired power plants instead. And the funny thing is that if you look down there at the list of waste, we actually get more uranium out of coal-fired power plants than we get out of nuclear power plants. And this is completely forgotten in the debate about nuclear, this waste profile. And it's sort of, when waste comes out of a coal-fired power plant, you are allowed to put all that fly ash outside the power plant on the parking lot, and if it's windy, then it can fly a little bit around, and some of it ends up at the neighbor's garden, whatever. And we don't worry about that. But if it's a nuclear power plant, then we worry like crazy. It's simply like super illogical. And I think again, Germany is also in this situation where you have to select between nuclear and coal fire. And I sometimes some of the things in the debate that I'm listening to, I don't really understand how the politicians get away with saying some of the things they say. But hey, that's my view, and of course I'm biased. So that concludes my presentation, and I'm really happy to take some questions.
One question, there is a Google Doc where some questions are already remarked. Is this still being followed, or shall we ask our questions through the voice channel? Right.
I hope that I already answered some of the questions why we want to go with thorium, because it has a better waste profile, and it has the possibility to create a fuel cycle with potentially have a breeder in the future, and also the waste profile is better. You don't need enrichment. You need a lot less mining. So those are some of the pros and some of the reasons why we want to use thorium. Yeah, that's of course always a good question. As you know, there's 31 countries around the world that have nuclear electrical power today, and most of those say that they have a problem with the waste, and the politicians in most of those countries are trying to find ways to handle that. And we're already talking to some of those countries, but of course that's under NDA, so I cannot give any details. But I think there's a good chance that politicians in some of these countries will choose a solution where they try to sort of recycle that spent nuclear fuel in waste burners in the future. I'm not sure I understand the question. So we do not want to remove actinides. We put the sort of long-lived actinides and the plutonium into the reactor, and then that's what is burned, and this is what makes it possible to run the thorium fuel cycle, because you need some kind of start fuel. So we do not remove it. We want to keep it in there until it has converted into fission products, and then of course we will remove the fission products. But in the very first reactor, we will not do very much work to remove the fission products. Yeah, so if you want to build a reactor in the thermal spectrum like we do, it's almost not possible. It's at least a very bad idea to use chloride salts. Chloride salts are better to be used for fast reactors and molten salt fast reactors. So chloride salts is sort of not on the table if you want to build a thermal reactor. But it's true that we could select sort of between a fly salt and a thorium, lithium fluoride, thorium fluoride salt. And the reason we chose to start with the lithium fluoride, thorium fluoride salt is because in Europe, and especially in Denmark, it's very difficult to get approvals to handle beryllium salts, and also it's a bit dangerous. So it's something that we didn't want to work with in the lab from the very beginning. It's not that we will. I mean, eventually we would likely look at FLIBE as a potential salt to use in our system. but we've decided to start with lithium fluoride, thorium fluoride, because it's much easier to get approval to work with that, and it's also a lot less dangerous to handle in labs and so on. So it's simply from a cost perspective, and a lot of the things we learn today using lithium fluoride, thorium fluoride, that also applies to flibe salt. So I mean, the learning process is just a cheaper way to learn the same things. Yes. Yes. So first of all, heavy water is a really, really good moderator. So, and when you look at moderators, I mean, a lot of people are looking at graphite as an alternative moderator. And the problem with graphite is that it's very expensive to buy the nuclear grade graphite. It has this problem that it's swelling over time inside the reactor, so it limits the lifetime of the reactor. It also gets quite radioactive, so it becomes a waste stream afterwards. And so it's expensive to buy, it's expensive to get rid of it. But in several decades ago, like back in the 80s and 90s, heavy water was quite expensive. But some of the latest research have actually made it possible to make heavy water at a much lower price point today than what it was 30 years ago. So this makes it cheaper to buy heavy water, but also after you end of life of the reactor, you can actually reuse the heavy water in your next reactor without doing any cleaning of it, and it's not radioactive afterwards. So the economics of using heavy water is simply better from buying it and processing the waste or the sort of the products after end life of the reactor. And also it would not limit us. The first reactors, we don't want to get them approved for 10 or 20 years because it takes a lot longer to get and is more expensive to get a reactor approved for long periods of time. So we want to start with a reactor that runs for a short amount of time, and it seems like 5 years is a good time span for one of the first reactors. So you also see that the molten salt reactor experiment that ran in the 60s also ran roughly this time span. So this is why we're starting with a 5-year expected lifespan of the commercial reactor. But of course, in the future, we hope that we can expand that to 10 years and 20 years and so on. And in that respect, heavy water is a very good choice for moderator because it doesn't limit that expansion of lifetime of the reactor. And then again, it also gives us some more safety because we can both dump the salt. When we want to shut down the reactor, we can dump the salt, but we can also dump the heavy water. So we sort of have two different fluids that we can dump. And it also gives us, when you have the heavy water, you can circulate that. So we pump that around and we pump it outside the core. And this is where we cool it down again and pump it back into the core. So it's, and of course, a lot of people say, oh, heavy water, it's you need to keep it below boiling point. And that's true. Because we don't want any pressure inside the reactor core. So we keep that water in liquid state at atmospheric pressure. So, keep it below boiling point or below 70 or 80 degrees. And in order to do that, we need to cool it quite a bit. And when you look at the amount of heat that transfers from the molten salt into the water, it basically consists of 3 different things. So there's the neutrons that needs to be slowed down. That is the major contributor to the heating of the water. And of course, you also have that in a graphite moderator. But in our case, so a lot of heat goes to slow down the neutrons. The second thing is all the gamma radiation that is stopped by the water. And of course, that also heat up the water. And then finally, you have the thermal transport of heat from the hot salt pipes into the water. But they are not in direct contact. There's sort of a vacuum or gas in between those pipes. So the thermal conduction from the hot pipes to the cold water is not very good, and therefore that is the smallest amount of contributor to heating up the water. Yeah. But the problem with light water is we could use light water, but light water, it does not allow you to do a breeder reactor. And sort of what we are preaching here is also that it is possible to make a breeder reactor in thermal spectrum. So this is also why we keep on pushing this heavy water, because that is what makes it possible to make a breeder in thermal spectrum. Yes, and the breeding ratio was very close to 1. Yes.
But was it not the shipping port reactor? Yes.
But we have also been looking at lithium hydroxide in the past, but we believe for the first number of reactors, it's a better choice for us to go with heavy water. That's not to say that maybe in the future we could use something like lithium hydroxide, for example. Yes, correct. The salt is still running at 700 degrees. When the salt exits the reactor core, it's 700 degrees. Yes, it of course depends on the reactor design, and we have looked at a number of different design. And for example, the 1 megawatt reactor test reactor, it's a very it's a much bigger number than in the 100 megawatt production reactor. So it depends on the design, but you could say it's sort of in the range of 5% of your energy. I think they. Yeah, there was some long time ago. There was some images predicting that, but that's not part of our design anymore. And we do this in a different way right now. And this is one of the things that I cannot go into details about. Yes, it is significantly less. And again, the heavy water does not scale linearly with the amount of output power. So the larger the power you have, the smaller percentage of heavy water you need. So again, with the 1 megawatt reactor, it's almost 1,000 liters of water to 1 megawatt. So so there the ratio is not very good, but that's also just meant to be a demo reactor. Yeah, this is not official. We're not sharing that information currently. This is something that we're debating a lot because, of course, it would be from a physics standpoint, you just want to get lithium with 5 nines purity. But of course, that's very expensive. So I guess in the beginning, some of the first reactors, we will not have a very good or like definitely not 5 nines. But of course, this is something that we will try to get hold of for breeder reactors. So again, we are on a sort of on a trajectory where we want to improve that enrichment more and more during the first decade of operating this reactor. Yes, correct. In the first number of reactors, we don't expect them to be breeders, so there we will not separate that out. But it is a possibility to separate that out. But of course, there's also a discussion about proliferation related to that. So that's also something that we need to discuss with the regulator. Yeah, this is more like maybe a political or maybe even a social question. I showed that image of that first Hanford reactor, which was it was built entirely from the ground up and started in 11 months. And this was back when they knew nothing. It was certainly not done on an assembly line production. And most of the people who worked on it didn't even know what they were working on. So that's amazing that they were able to do that in 11 months. I also showed the other reactor from Finland where it's not so amazing, the progress. One more thing I want to point out is there's really big international medicine companies or pharmaceutical companies who are trying to get vaccines approved for the last several decades, and they wanted to do it in 8 years or 6 years, and they spent billions of dollars to try to reduce the amount of time that was needed to get a vaccine approved. And then suddenly in 2020, it was possible to reduce it down to less than half a year, just from one day to the other almost. And that was, of course, not because of physics or math. It was purely because the politicians changed their mind or the public changed their mind or whatever. And of course, this could also happen with nuclear reactors. I mean, today it's very cumbersome to get the approvals to install a nuclear reactor. But that doesn't mean that this have to be like this for the entire future. Of course, we look at, is it possible to manufacture these reactors on an assembly line and manufacture more than one every day? And when you look at car factories and airplane factories and stuff like that, it's clearly possible to manufacture more than one of these every day. So that's not an engineering problem. But of course, will you be allowed to install them with one every day? And that's a political and a sort of a social problem, and it can be made possible. Whether it would happen within the next 10 years, I doubt it, but I hope that in the next 20 years, at least we will be able to move in that direction. Yeah, yes. Yeah. It's not like we start in the morning and have all the parts and then we assemble it all. Like it's an assembly line, so maybe we start like several months before it's supposed to be finished. We start, getting the parts into the factory, and then as it moves down the assembly line, then it gets assembled more and more. But the process is that you move everything on the assembly line at least once a day to the next step.
Ja, Evelyn.
Yes, I'm sorry I didn't get into this during my presentation, but this is one of the places where Copenhagen Atomics is also quite different from most of the other reactor developers, is that we only want to develop that box with the nuclear reactor inside, so all the radioactive parts. We do not want to supply the sort of the power plant and the steam generator and all the like the parking lot and the fence around and all that good stuff. We believe that there's other companies around the world that are much better suited to build the power plant and run the steam generator or whatnot. And we are sort of agnostic to what people are using. The output from our reactor is hot salt. And whether people use that for generating electricity or for industrial heat or something else, we don't mind. And we want to make collaboration with other companies and consortiums, and they are going to be the ones building the power plants. And like you said, a molten salt reactor is very good at load following, but I actually think most people will want to run it at full power most of the time. So I want to give one example. So of course, with wind and solar, you have these peaks whenever the wind is blowing in the middle of the day when the sun is shining. You have more of it, and then you have nothing during the night. But with molten salt reactors, instead of trying to load follow and do the opposite of the solar power plants, then what you will do is just you will run your reactor 24/7 at full power, 100% power, and then you will put all your salt into a big storage tank, a molten salt energy storage, and then the people operating the generator, the electricity generator, they can decide at what hours of the day to take out the energy from that big storage tank. And we actually did some calculations for the Danish electricity grid, because in Denmark we have a lot of wind power and we have prices of electricity going up and down and even sometimes going into the negative area. And it turns out that if you take 4 days, like a sliding window of 4 days during the entire year, and then during those 4 days you sell all your energy at the peak hours, like the hours where the electricity price is the highest, then your average price from selling it from nuclear power will be 4 times higher than the average price from the wind farms. So it just goes to tell you that we can get a much better economics by storing this in molten salt tanks and then taking the energy out of it when the price is at its peak. But of course, if you do that, you have you're not using your steam turbine or whatever you use optimally, because it's only running part of the time. Anyways, that was a little bit of sidetrack, but I think most of our reactors will run full power 24/7 for 5 years or whatever is the lifespan of those reactors. Yeah, I talked about that a little bit before, and it's basically if we were trying to get a reactor approved for 20 years right away, it will take 5 years more to get it approved. So it's sort of shooting ourselves in the foot. Yeah, I think it's a lot more important to get something online and show that it's working, and then gradually, as we show that it can run longer than 5 years, then we can increase the approvals to run for 10 or 20 years or whatever. Yeah, that's true, but this is a little bit different because this is very high temperatures and very corrosive salts. So we need at least some records to show that it can last longer than 5 years. Either it means but basically what comes out of the reactor is the salt, a stream of non-radioactive salt, and once the heat has been taken out of that salt, it's returned back to the reactor and heated up again. But of course, they might also mean the passive heat removal system. So sort of in a shutdown scenario, how do you remove the passive decay heat? There's a number of different systems for doing that, because we need to have if one system fails, we can rely on another system. So yeah. Yes, correct. And this is part of the reason why we're currently co-located with Alfa Laval in Copenhagen, and part of the reason for that is Alfa Laval is the world leading manufacturer of plate heat exchangers, or stainless steel brazed plate heat exchangers, and those heat exchangers are particularly well suited for molten salt reactors. So this is why it's very interesting to be working with Alfa Laval. Yes, correct. As soon as we shut down the pump, there's both a pump that pumps around the molten salt in sort of the primary fuel loop, and as soon as that pump shuts down, the salt would automatically drain back into the dump tank, which is sort of part of the loop. And for the heavy water, it's a similar situation. If the pump stops, then the heavy water will drain outside of the core region. Yeah, it's funny, but a lot of people sort of stumble over this or make notes about it. And so, when you know classical nuclear reactors, in order to be an operator in one of these reactors, you need to learn a lot of procedures. And those procedures are very, very well documented. And in order to get that reactor approved and started up, there needs to be a procedure for everything that people can possibly think of that could happen. So I mean, and also these people who sit in control rooms today, we know that they cannot be a full alert all the time. So we've already implemented computer systems that give alarms if some value goes too high temperature or too low temperature or too high pressure or whatever. So already today we're sort of relying on computer alarms, and then when some alarm sounds, we're relying on people following very strict instructions on what to do. And I mean, computers are much better at following strict instructions when alarm sounds. So I mean, I believe, or we in Copenhagen Atomics believe that we actually can create a much safer reactor by implementing all these procedures in software. And of course, then if somebody says, "Oh, but I don't trust the computer," of course they can put a human there and they can put a stop button, and then the human, they can have all the alarms they want, and they can look at all the different screens with all the different numbers they want. And if they see something that is outside what they feel is safe, they can push the stop button. And what will happen then is that the two pumps in the salt pump and the heavy water pump will stop immediately, and we will dump the salt in the water, and everything will stop within a few seconds or 10 seconds. So and that's one of the reasons why molten salt reactors is more safe than light water reactors, because they're really easy to control, and even if there's no human, then it's also walk away safe. So eventually it will shut itself down. So we don't see that there's a need for a control room, but of course if the regulator or the public wants some person to sit there with his hand on the stop button, that's okay with us. Yeah, so this is similar to spent nuclear fuel in light water reactors. So when the spent nuclear fuel is end of life, then it's taken out of the reactor core and is put into a sort of a fuel pond or a big pool of water where it sits there for 10 years or more to cool down. In most reactors around the world, it ends up sitting there for 30 years or more. And this is sort of the same with our reactor, that of course, right after it has been running, it's highly radioactive, and you don't want to transport it on a truck. So you put it aside and let it sit there for a number of years, 10 years, 20 years, to cool down radioactively. And then once it has reduced the amount of radioactivity, then you can move it. Same way as you move spent nuclear fuel today. So it's not much different from light water reactors. Yeah, you would probably need to put a lead shielding around it when you transport it. And of course, that also depends whether you transport on truck or on ship or yeah. It's most likely that the fuel salt itself will be when the reactor shuts down. Then the fuel salt will be pumped into the next reactor, so the next version. So the fuel salt is already taken out of the reactor right after it shuts down. It's an empty reactor. It's sort of just a stainless steel and cables. Yes, correct. Yeah, definitely not. It's when the reactor is loaded with fissile fuel, then it's sealed and welded sealed, and it's not supposed to be open in any way for the entire lifespan of the reactor. And it's even supposed to sit underground, so sort of in a concrete shaft underground, and there's no human access to the reactor while it's running for those, say, 5 years. This is also one of the things that makes it safer. And this is one of the things we believe will make it easier to get approved because there's a lot of, in the approval process of sort of other types of reactors today, a lot of that approval has to talks about how the personnel have access to the reactor and what can happen and what they can forget. They can forget to close valves or whatever. But we don't have that problem. I mean, when the fuel is loaded, potentially there can be inspectors from IAEA or some other regulatory body. They can be there when the fuel is loaded and the reactor is getting ready to turn on. And then when it turns on, it's deep below ground and it's nobody touches it before its end of life. So there's at least 3 barriers between the salt and nature, so that there's 3 containments around the salt, you can say, and there's still some debate exactly because the reactor wall itself will not stop all the gammas and the neutrons. So like I said before, it sits underground inside a concrete shaft, and that concrete will get some doses. And this is some of the things that we're still debating and where design might change. There's many possibilities. Our job is sort of to limit the amount of choices and try to find the thing that scales the best, both economically but also in terms of deploying this fast. Um, Not right now, but yeah, as you know, there's already several companies pursuing fast molten salt reactors, and of course that's possible. But like I said in the beginning, I believe it's much more difficult, and this is the reason we chose thermal reactors. But of course it's possible, and who knows? I mean, if several of these companies have success and show that it is actually possible to do fast reactors in an economic way, and it's possible to scale, then I mean that I don't know what will happen in 10 or 20 years from now. Yes, of course. Again, it's also possible, but again, we're looking at where the big markets, and the big markets are definitely in Asia and Africa. And if you can find a way to supply a lot of energy to them in a way where it can be deployed at low cost, I think there's a lot more revenue to be made there than there is in Greenland or in the Antarctic or something. This is a long debate about what people think different solutions costs. One of the big questions is, of course, what is it going to cost to get this approved? And also one of the things I talked about before is we want to burn spent nuclear fuel, but even though we've asked in several countries, it's not possible to get a price tag on that. Also, it's not possible to get a good price tag on lithium-7, for example. So there's several of the sort of the expensive components where the price tag is not very accurate yet. But if you look at it from like a top-down view, I mean, the stainless steel that is used, or whether we use other steels, the price of those are well known, and it's a small percentage of the overall cost. All the sensors and electronics and all that good stuff is also not. It's a small percentage of the overall cost. And then, of course, there's the fuel salt, especially the lithium-7, the heavy water, and the plutonium, and nobody knows exactly what that's going to cost. There's also the approval. Nobody knows exactly what that's going to cost. So depending on what prices we can get over the next 5 years, we can give better and better estimates of what a final reactor will cost. But the thorium itself, for example, is not very costly at all. So thorium is sort of a byproduct of mining we already do today. So that's definitely also a very small percentage of the overall cost. And some of the things I mentioned there that were some of the expensive things like lithium-7 and heavy water, they can be reused from one reactor to the next, to the next, to the next for more than 100 years. So the economics of those materials is different than the economics of, for example, the stainless steel that have to be recycled after each reactor lifespan. And that plays into sort of the overall economics of this reactor. And then, of course, the most important thing is that the amount of R&D and the amount of capital that goes into building this on an assembly line is a very large amount of capital, and that needs to be serviced. And that's also a big part of the sort of the expense. And there we look towards investors and ask them, like, what is the sort of the return on investment you want for this investment that can create this factory? It depends on the risk, right? So if politicians lower the risk for nuclear power, that also means that the cost of the money from the investors will be lowered significantly. And so there are many things that plays into the cost. And the only thing we say is that we definitely work towards making this type of energy cheaper than any other energy form that you can think of. We want to be able to beat any other energy, including fusion and wind and solar and everything. That is our goal, and I'm very positive that we will reach that goal with assembly line manufacturing. Yes, this is the thing that we are not selling the reactors to the customer. We are selling the heat that comes out of the reactor. So basically, it's a contract with the customer, the power plant, and the power plant is buying the heat, and we are operating the reactor, and after end of life of the reactor, we will take it back and recycle it. We also own the fuel salt. We are just selling the heat as thermal energy. Yes. Yes, and this is true. It's sort of not only a new reactor, it's also sort of a new business model for the nuclear industry. But we've seen these things in other industries, and the way we look at this transition is I think like I said in the beginning of my presentation, we humans have been used to the same sort of energy market now for 3 or 4 or 5 decades, where fossil fuels was the primary energy source, and there was a little bit of this and that next to it. And we've sort of gotten used to it because for most of us, it has been this way for our whole life. But that doesn't mean that it's not going to change in the future. And if you look at energy is a really, really important ingredient in almost any other product that we manufacture, or at least in the factories that manufacture those products. And today, for example, the oil and gas industry, the revenue every day from the oil and gas is more than $10 billion. So that's a big number. But this energy allows other industries to make a lot of money, and there's different opinions on how much, but I think everybody can agree that the amount of revenue from industries that are heavily depending on energy is at least 10 times higher than the revenue from oil and gas. So that means that's $100 billion every day, or it's more than $100 billion every day. And then if you look at this growth chart that I showed in the beginning, where everybody expects that the amount of energy produced in the world will double over the next 3, 4, or 5 decades, and most of that is in Asia and Africa. That also means that there will be at least a new market for $200 billion every day of goods and services, mostly goods, that rely on energy prices. So if you take that view of the energy market, that every day there's a new market, well, it's not every day, but the amount of revenue every day from that new growing market is $200 billion, then this discussion about who funds the reactor, like who is the investor? Is it or who's paying for the reactor? Is that the customer, or is that the investor in Copenhagen Atomics or some consortium? It becomes irrelevant in that sense. The question is, of course, where is the risk? And of course, you could argue that the risk might be smaller if you let some companies somewhere in the world who have never built a nuclear reactor before, let them buy it and operate it. Then the risk would be smaller, versus having the company who is actually building these reactors also operating and recycling. I think the risk is smaller in our business approach, but the future will have to show that. Yeah, especially after COVID. Yeah, it is, and it's of course we in Copenhagen Atomics take it upon our shoulders to try to fix this. We those of us in the world who wants to see more nuclear, we have to reduce the risk for the investor, because that's the reason why the money is going elsewhere, is because the risk in investing in nuclear has been too high in the past. So the main thing we have to work at is reducing that risk, and once we reduce that risk, we will see more money invested in nuclear. And part of reducing that risk is to talk to the public about the facts. But that's easier said than done. And we definitely need not only us in Copenhagen Atomics, but we need all of the people around the world who are pro-nuclear to help change that situation. Yeah, so our main funding is from private investors, but we sort of have 3 different funding legs. First of all, private investors. Secondly, we do research. We apply for research grants, and we do research together with universities and national labs, and that gives us some income, which is called sub-funding. Some of that is also loans. And then finally, we have revenue. We are selling these molten test loops that we're building, and we're also selling some of these, especially purified salt that we're making in Copenhagen Atomics, and that gives us some revenue. So we have those 3 different revenue streams or access to money. So that this is what makes it possible to grow the company, and we've been very fortunate that we were able to sort of hit the market at the right point in time and make these purified salts available right at the time when universities and national labs were also getting ready to buy these salts. And when if you want to buy these salts from regular chemical suppliers, the quality you get is not enough for what you want to use for molten technologies, whether it's be reactors or test loops. So you basically need to purify it yourself, and of course most people in universities and national labs do not want to learn these tricks, so they much rather want to buy it from us. Yes, it also helps us to scale up our own production. So if we can sell 10 times more salt than we need ourselves, then of course we get a good economic of the salt production we need for our own experiments. That's true. That's true. It's also one of the examples is sort of the mobile phone industry is Samsung, for example. They are supplying the screens to other brands like iPhone, for example. But they are also one of the competitors because they also make their own smartphones. And so it's yeah, like you said, it's been done in many other industries before. And of course, we can be both a supplier of some of the few components that we are really, really good at, and also develop our own reactor concept. Yes, of course. We do believe that most of the reactors will be installed in parallel with 10 or 20 reactor containers at the same site. I mean, it would be preferable to us to make deals with people or power plants that can take several reactors rather than having to interface with sort of power plants that can only take one at a time. I think eventually we will get into a market where we will sell or not sell but set up reactors and sell the energy from one single reactor unit at each site. But I believe that in the beginning we will prefer to go with sites that can take many reactors at the same site. Yes, this is true. But it is something that we are researching, and we know that the molten reactor experiment ran without any significant problems related to this back in the 60s for 5 years or more. So it is a small problem, but it's definitely not a showstopper. But it is likely something that we will have to show to regulators what is the extent to which this happens. And especially it happens in the heat exchanger. So some of these, especially metals in the salt, tend to plate out on the cold surface in the heat exchanger. And there are actually several universities and national labs who are also researching this particular thing. And by the way, this is an issue not only for the type of reactor we are building, but it's any type of molten reactor, whether it's a fast reactor or thermal reactor, or chloride or fluoride. Yeah, yeah. First of all, we don't want to give any exact details, and it also depends on the exact reactor design, so the size of the reactor, whether it's the 1 megawatt or the 100 megawatt. But I would say more in general terms, we do expect that the first of these reactors will be started on a site where there's already spent nuclear fuel. So the fuel will not have to be moved. It will be converted to fuel for our reactor on the reactor site where it's already located today, and it will be loaded into our reactor, and then that will be started there. So everything happens inside the fence. So that sort of solves the proliferation problems. But that's not to say that it's free of problems. I'm sure this will create a number of meetings and questions and yeah. Yes, and this is something we are actively discussing with different countries and different partners right now. But most of this is under NDA, so this is not something we can share here. Yeah. So again, it's this is sort of I think you refer to some of the reactor design showcases that we've shown online. In the long term, when you want to make a breeder reactor, you have to remove all the sort of the neutron poisonous fission products from the salt stream. So that's quite a lot of the fission products you have to remove if you want to get a really good breeder ratio in your reactor. But in order to just start a reactor and show that it's working, then you don't need to remove any of the fission products. So it's sort of it's something that we want to improve over the first many versions of reactor and get a better and better neutron economy in our reactor. And one of the things we have proposed early on was a system where we remove the fission products by spraying the fuel salt in very tiny droplets, and by doing this we can remove all the gaseous and all the volatile fission products from the salt. And we've done some simulations early on, and it shows that you, without doing wet chemistry, you can remove in the order of half of the fission products from the salt in this way. So this is very promising because we believe that it will be very difficult to get approvals for doing online reprocessing or online sort of processing of the fuel salt with sort of wet chemistry or even electrolytic or electrolysis. Some of these techniques that are oftentimes used in the lab when you do chemistry, it'll be difficult to get that approved inside a reactor, at least from the beginning. I do believe that the world is going to change in the next 20, 30 years, and eventually this will become a possibility, but not from the very beginning. Yes. Yes, we've done some experiments, and we are going to continue to do more experiments. And we also did some simulations. And it's not an explosion, but it's true that we, in a worst case where you have sort of like a missile or a bomb landing directly in the core of the reactor, then of course the water and the salt will mix, and you will have steam generated. But so far, in any scenario that we've come up with, the system we have is able to keep that steam inside the second containment. So it means that it never gets outside of the building. But of course, if there was a missile that created a hole in the building, it's a different story. But I mean, the other reactors are also not missile or bunker buster safe. So there's no reason to believe that our reactor should be bunker buster safe. But we did simulate this, and it is possible to contain the steam in most accident scenarios. And we believe that what we have now can be approved I have to say that it's a little bit. So all the time we show this one box that is where the reactor is housed inside a 40-foot shipping container. But there's actually a little bit of auxiliary systems, both for decay heat removal and also for this. If there is sort of a steam generation inside that box, then there is a burst disk and there's another containment that can sort of turn that steam back into water. So there is auxiliary systems to deal with some of these issues. Yes, but again, it is true, and this is part of our simulations. But again, you have to remind yourselves that in a light water reactor, you have many more liters of water, and at the same time, that water is under pressure. In our case, it's not under pressure, and we have sort of in the order of 1 ton of water or 1,000 liters of water, and of course that turns into a lot of steam. But if you can remove that to another containment that is big enough to hold that steam, then you don't need to break the containment. But it is true that if that were to happen, then the reactor core is basically dead, and you can you would have to send it to for recycling. But you would the important thing is you would not kill any humans or send a big radioactive cloud into nature. Yeah, we will likely make some demonstration for a regulator, and we can do that, of course, with non-radioactive salts. Yes. Well, yeah, it's true that we cannot test everything, but we can definitely test many of the things, and we try to make tests that sort of simulate what would happen inside a reactor, even without having the chain reaction running or without having the radioactive materials. So I do believe that sort of upwards of 80% of the testing can be done in a non-radioactive environment. But it is true that there are some tests that need to be carried out when you turn on the reactor for the first time, but also over the. I mean, when you develop the reactor from a sort of a test reactor up to a commercial reactor, and then continue to do more advanced reactors that are getting a better and better breeding ratio, we will continue to do a lot of testing in the future as well. Yes, great. Yes, definitely. This is also part of the reason we built the loop, and we already have collaborations in several countries where we're discussing this, but we've not yet sort of been able to put a loop inside a reactor. But I expect this will happen, yeah, hopefully sooner rather than later. But again, this is some of the things that are under NDA, so I cannot share details. But yeah, definitely we want to make loops that can go into a reactor, and there's several different formats that this can take. Yes, yeah, there are. Yes. No, not ourselves. We've not been able to do materials tests inside neutronic fields or inside reactors yet. It is something we want to do, but right now we rely on research being done by national labs and universities and the like. So yeah, literature, the publicly available literature on this tests. Yeah, it's not my area of expertise, and there is a lot of debate in this, and I know we have people on our team with strong opinions, but in general, I would just say that this is something that where we also still learning. Yes, correct. It's actually it was a project that already finished. It was funded by the EU, the research budget in European Union. But there is a follow-up project that's called Samofar Safer, or Samo Safer, I think it's just called. But again, it's sort of the same topic. It's researching the safety of molten reactors. And it's right that one of the reactor designs they are particularly interested in looking at is a fast reactor, but with the fluoride salts. But anyways, in general, I want to say that it hurts me a little bit that we see too little progress in Europe in terms of research in molten reactors. We've seen a lot more uptake in the US and Canada, for example, and other places like China and India. There's government-sponsored projects, and when you look at how promising this technology of molten reactors are, I think it's a shame that the EU and the countries in EU is not spending more money on research in this field. Of course, it's great that there's this one project you mentioned, Samofar, and the follow-up Samo Safer, but we should have 10 of those projects by now. And I think in Europe we need to learn to become better at cooperation across borders, and we need to. I think we need to work together much more across Europe to drive this agenda and get more research funding for this. I mean, of course, there are a few startups in Europe that are working on this, and I'm sorry to say that it's much easier for us to get collaboration outside of Europe right now than it is inside of Europe, and that's a little bit sad. But also we already saw one startup, Moltex from the UK, that sort of moved most of their activity to Canada, and I fully understand why they did that, because the climate in Canada is just much better for funding and doing this type of technology development. But I think in Europe we really need to get our act together and sort of all of us who are active or pro-nuclear, we should work together and try to create common grounds and make more collaboration and get more funding and get on the agenda more, and find some politicians that will help fight our fight in the parliaments and the EU and so on. I really think that there's there is much more potential in Europe, but we are not very good at getting something out of that potential. Yes. We believe that the green taxonomy thing is really important, but I have to admit that we have decided to focus our the amount of resources we have are small, and there's a long way till we have an assembly line of reactor production. And I think we should focus our efforts on what we are best at, and that is building technology. And then we hope that there's other people in Europe who will help drive this taxonomy agenda and all these other questions. But it's definitely important, and I really hope that there's other people who are working as hard as we are, but on those subjects instead. No. The funny thing is that we have been invited to talk to politicians both in Canada and the US, and we didn't even contact them and ask them to get an invitation. They asked us, but in our own little country, Denmark, we have asked the politicians several times to get a chance to present, and we've only had one chance to present, and that was sort of not many politicians showed up. So that just shows that there's almost no interest in this here. There are a few politicians, but in general, it's very little. It's if you look at the public, there's a lot more people who think we should consider nuclear. But it's not close to 50%. It's still a minority that are pro-nuclear. But it has definitely increased very significantly in the last 5 years, and especially the last 2 years. The debate has changed a lot in Denmark. But still, the politicians, they sort of look at when is the next election, and is it likely that I can get a lot of votes if I go pro-nuclear? And I think most of the politicians, almost all of them, have concluded that it's not a good idea yet to go pro-nuclear. There's many other things like cats and corona, whatever, that they can sort of brand themselves against. So those issues are more important to them. Yeah, but even it's not like they're standing up and being anti-nuclear. They basically don't want to touch that field because they know it's a difficult discussion, and they would much rather discuss cats or corona or something. Denmark used to have 3 test reactors in the past, or research reactors, but we've never had nuclear power production or electricity production in Denmark. There was some plans in the late 70s and early 80s to build a reactor here, but it never happened. We get sort of like 13% of our electricity in Denmark from Sweden, and so 13% of the electricity in the Danish grid is nuclear energy coming from Sweden. So it's sort of we still have a significant percentage of nuclear electricity in our grid. But I don't think there are any plans to even make an approval agency. And of course, if there's no agency to approve a reactor, then you can't really be allowed to start it. So no, I don't expect us to start a reactor in Denmark anytime soon. Yeah. Yeah, I don't know the exact. I don't know the exact details, but I doubt that it would be possible to do it in Denmark. At least, I mean, it's not that it's impossible, but it's just it would likely not be fast or economic to do it here. No. We ruled it out basically from the beginning. I mean, our neighbor country is Sweden and Germany, and just those two neighbors, I think there's much better chance. But things can change in Germany as well. You definitely have a proud nuclear history in like 70s and 80s and so on. Yes. 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 I will not discuss the salary range publicly, but we of course we want to be competitive with salaries you can get elsewhere. So I mean it's a market, and of course we want to provide a competitive salary in that market. Yes, we are looking for materials engineers, nuclear engineers, all of the above, chemical, material science, structurals. Engineers, all these type of engineers. On our website, there's a number of job posts, and they get updated regularly. So new jobs are coming online, and if you are sort of a nuclear engineer or any type of person with a technical background and a strong interest in this new field of molten salt reactor, I mean, you can also apply an unsolicited application and just say, I'm a really good welder or electrician or whatever it is you're good at, and apply for a job. And there's a chance that we might have a job, maybe not the first month, but maybe a couple of months later, because we are hiring people every week, and this will just increase over the next couple of years. So we will continue to need to increase our team, and we want some of the best people we can find in Europe. And even in the US, we are also sourcing people in US and Canada and so on. Yeah, feel welcome, but I also have to run soon. But it's been very nice conversation, and I hope that some of the answers was helpful in understanding what it is we're doing here. Thanks.
Now, yeah, if there's no questions, then I also want to thank you. It was a really good presentation, and I actually, let's say, I'm a very skeptic concerning thermal spectrum molten salt reactors. I just like fast reactors more, but because you presented your project or your reactor design so well, I actually start to be interested again in that subject.
Yeah, thank you.
May I say something?
Yes.
So, regarding the neutron spectrum, I myself, I like fast reactors, but I can understand why you would grow in this area of thermal reactor, especially when you have molten salt reactors, a reactor with liquid fuel, because essentially when you have a thermal reactor, you can have relatively easy control of the reactor by controlling the amount of salt of the fluid in the moderator, which you can't really have in the fast reactor, because the reactor zone can be essentially everywhere where the fuel is. So this is you get very good control over the reactivity of the reactor. Also, when you have a liquid moderator, you can drain the moderator. You have an additional way to cram the reactor. I'm I'm a bit concerned about essentially using water as a moderator, because it allows water can boil, can create pressure if something goes wrong. Also, if one of the pipes in the calandria breaks and you have the fuel salts dissolving in the water, that is something that would concern me. I would probably go for the graphite moderator and essentially do a design where you can change the graphite moderator, or where swelling or deterioration of the moderator would not affect you as much. For example, like in the sodium reactor experiment, the 60s, where they had removable moderator cans that after they had suffered a meltdown accident, they switched out the moderator can. And essentially you could do something like this with a removable moderator design as well. But I trust you have done your research on the topic regarding the choice of moderator, and I'm not really comfortable with that, but I think I'm looking forward to be proven wrong. And good luck to you.
Thank you. And we welcome. As you know, there's many different molten salt reactor flavors, and we welcome many different people with different designs pursuing. Getting those designs brought to the market. Of course, when we started this journey, we sat down and we looked at all the different options, and especially we looked at the economics in the different choices. And this is what led us to choose the heavy water moderated version. Of course, we also see that other options are possible, but we just like this one, and we hope that other people will pursue other options. And of course, we welcome the competition, and hopefully our design will prove that we made the right choices, but only the future can tell. And again, with regards to fast reactors, I try to sort of say what we like and dislike and why we made our choices, but again, I hope other people will try other types of reactors. There's, with regards to this the safety issues, there's maybe you've also seen that there's a number of companies who wants to put reactors on ships, and we've also been asked by several ship operators to suggest some solutions for ships. And again, like you were worried a little bit about water and salt, I'm worried about fast reactors on ship, but that doesn't stop other people from pursuing that. And we just have to wait and see what works well, both from a technical point of view, but also from an economics point of view.
If you have a molten salt fast reactor or a gas-cooled fast reactor in a ship, it's essentially some kind of fast reactor where the water can displace the coolant. Then you get a really big problem, because as soon as you get that moderated, it will get prompt critical. But I think when you have, for example, a lead-cooled fast reactor, when you have then a reactor breach, the lead will just freeze and protect the fuel rod from the water, and will not make the reactor supercritical.
It is.
No, I mean, I agree. I agree there. I mean, the molten salts on the ocean or on the sea, I don't know. It really doesn't sound like a good combination.
Also, liquid sodium reactors on the ocean.
Absolutely.
And I'm saying that
Absolutely.
I'm saying that as a fan of sodium reactors. I would never put this on my ship.
But I think you know that there's already been submarines with
yes, and I think it was a good idea that this was discontinued.
Yes. All right, but it's sort of besides the topic. I think we could talk about that for a long time, but I would really like to run within a few minutes. So if there's like one last question.
Yeah, I've got one. How are you going to regulate the power level of the reactor if you don't want 100% or 0% power?
Yes. First of all, you turn down the speed of the primary fuel salt pump, so that the fuel is or the fuel salt is flowing slower through the reactor core, and that decreases the power right away. And if you need to adjust the activity of the core, you can also lower the level of heavy water, sort of the height of the heavy water in the reactor core. Then you then you decrease the reactivity.
Do you have watts? Control rods? Do you have control rods at all?
It is possible to put control rods there, but it's actually not needed. You can easily control the reactor with the heavy water, sort of the height of the heavy water and the speed of the two pumps. It can easily be made safe. But if some regulator says that they really need a control rod there, then we can put one there.
Yeah, especially for shutdown, you could also put easily poison in the heavy water, like boric acid, or like in the Candy reactors, there is the option to put, I think, gadolinium hydroxide or something like that in the water.
Yes. All right. Thank you for all the questions and the debate, and I hope maybe someday we can come back and show some more details.
Thank you very much. I hope we can visit your test reactor.
Good luck.
Okay. Good luck.
Thank you. All right.
Yeah. Thanks for the great presentation.
Yeah, I don't know if there's more questions, but I will do my best to answer them if there is any.
Oh, I guess your audio quality is not the best one. Thomas?
Do you have heavy rain in your background, or is it just noise?
I think I'm sorry. I try to solve it, but there's so much noise here, so I will prefer to answer it in writing.
Ah, okay. No questions? I mean, there have been a lot of questions and they have been answered pretty well.
Yeah, exactly.
I want to ask something about the waste storage.
Yes, Noah?
I think what they plan is essentially to extract the fission product from the molten salt continuously, as far as I've gotten that. Is that correct?
So it depends on the version, I guess. Thomas?
Sorry, could you repeat the question?
So, regarding the fission product that will occur in the reactor, so what you essentially plan is removing the fission product, not the actinide, from the salt mix.
Yes. So there will be an inline removal, as Thomas explained, with the spraying system. That is one way, and we are working on several other ways to maintain the salt quality.
Okay, and the fission products, will they be stored on site? In what way?
It will be actually stored within the container. So the amount of fission product you have to remove is not really excessive in terms of mass or volume. so they will be stored within the container. During the operation, there will be no access to the container.
Okay, and you essentially plan to leave every actinide forming inside the reactor in the core during the operation.
Yes, it's only the fission products that will be removed. The actinides will eventually be burned. It will take time, but eventually they will be burned.
So, since this is a thermal reactor, burning the actinides will take a lot of neutrons that will need to transmute the actinides into uneven nucleon numbers, right? Will there be a problem with essentially having too many neutron poisons in the form of actinides at some point in the core, with the actinide number mounting over time over the operation?
It depends. When you want to make a breeder with the protactinium removal or extraction, I think that could solve the problem. But the first versions will not be a breeder. Now the quest is to get the first reactor online, and then the subsequent versions will be moving towards having breeder reactors.
So essentially, it will be no problem keeping the reactor critical with an increasing amount of actinides in the core, but essentially it will be a converter reactor, breeder reactor.
Yes, that's correct.
Okay, and when you decommission the reactor, as far as you said, is that essentially what you plan is to essentially decommission the reactor as a whole, and only then take out any waste except the fission product. And when you will decommission the reactor, there will, you will probably burn up some actinides, but you will still have actinides in time when you decommission the reactor. And will those actinides, are you planning to store them? Are you planning to put them in follow-up reactor?
They will go into a follow-up reactor, and but there again, time will show. Also, it will depend a bit on what you can get approved from a regulation point of view.
Okay, and the fission products, they will be stored sealed in glass or sealed in temporary storage?
That has not been decided. Again, it will require standards to be written, and so that is kind of out of our hands. So that is the AIA that will set the standard for how to handle.
Okay. You said that the first reactor will be the first test reactor will probably only be operating for 5 years to test out the component, just based on the experience gained on the first test reactor. And you said that the following reactors would probably be lasting around 10 or 20 years. So if you have a reactor that essentially lasts 10 or 20 years compared to, for example, temporary light water reactors which could last 50 or 80 years, you will create essentially more waste reactor material, which will probably be counting medium or lightly radioactive waste, which needs to be stored. Are you planning for that?
Yes, of course. This is a kind of a difficult topic to cover here, especially with a lousy microphone. But the main part of a traditional light water reactor is not the nuclear part, that's the concrete. And given that this is a fairly low weight steel construction, and steel is like fairly easy to decommission. So the total amount of waste, even with fairly short lifetimes, is going to be rather insignificant compared to the amount of energy used.
Okay, but you will have to need some sort of biological field around the reactor, which in most reactors is made out of concrete. So what biological field around this reactor module do you plan to?
Oh yes, the actual waste burner container will be operating underground in a concrete shaft. So and the shaft will be reused depending on how long time there's going to be energy production on that actual site. So there will be a concrete structure there that will be reused. It's only the container that will be recycled and decommissioned.
So essentially, the main mass of the power plant can essentially also be operating for 80, 60, 100 or more years when you essentially just replace the reactor module and put it inside the same biological field and building.
Yes, that's correct.
Okay. How long would it take to essentially remove these reactors? Because as far as I know, switching out reactors hasn't really very often occurred. There was, I think, some submarines, for example, the Seawolf had the original Thorium reactor removed for a PWR. And it's not you, it's multiple molten salt reactor companies that essentially want to combat the problem of the material problems of having a molten salt reactor by essentially changing out the cores. And this is something that I kind of worry about because it hasn't really been demonstrated very often, especially with this type, which had never been demonstrated at all. So this is something what kind of concerns me because, for example, the photon reactors, they have essentially a double reactor. One reactor module operates for 4 years, and then they have in this little barge that they plan to construct another reactor which operates for 4 years, and they essentially wait almost the entire 4 years, letting the reactor with all its actinides and fission products decay, so it can be more easily be removed, then only put in a fresh reactor module, and then take the replacement module offline. Then will wait for 3 years, and then will be removed. So when, for example, when I have my Copenhagen Atomics power plant, and it has operated for 20 or 10 years, and I want to remove the reactor module, will it take time for the reactor module essentially to cool down, or will you be able to remove it right away? What are you planning regarding this?
Yeah, we have a similar approach. So there will be room for more than one module in the shaft, and so the cycling time and it will be standing there to cool down. So you will just remove the fuel salt, pump it into the next reactor, or simply let it sit with the reactor, and then once it has cooled down for a number of years, then it will be removed.
Thanks. That was what I asked. Thank you.
Okay. I think that's it for now. So if you want to finally go, you can.
Okay. Okay, thank you very much for your attention, and we hope that we can join you in a physical meeting sometime in a not too distant future to have more discussions face to face. And it's been a pleasure participating. So good night.
Thank you. Good night.
Thank you. Good night.
Thank you also. Good night.